Hi everyone. So today we're going to be looking at powers of complex numbers. So that's going to be z to some power n. Now, before we get to that, we just need to go over the polar form of complex numbers because that's going to make our calculations a lot easier. Okay, so what is the polar form of a complex number? Well, we know that we can draw the complex plane with the real and imaginary axes. Then any complex number, z in the complex plane, can be written as some real part x and some imaginary part y. And then that gives us z is equal to x plus ry. Okay, that was the Cartesian form that we looked at in the beginning. If we want to look at this in polar form, it's pretty much the same as looking at this in terms of polar coordinates. So what we can do is draw a radial line from the origin to the complex number. We call that r. The angle that it makes with the real axis, we call that theta. And then that gives us the polar coordinates of this complex number. So now we can write z equals x plus ry. But we know that in polar coordinates, x is going to be r cos theta. So it's going to be r cos theta plus r times y, but y is going to be r sin theta. So we have r sin theta. And we've got r on both terms, so we can factor that out. So we get r times cos theta plus r sin theta. So we call this the polar form of z. Yeah, because it's just z written in terms of polar coordinates. Okay, so let's look at an example. So let's say we have z is equal to 1 plus r. So 1 along the real axis, 1 up the imaginary axis. We got that point there. Okay, so we need to find two things. First, we need to find r, the value of r. And second, we need to find theta. Then we can put that together to get the polar form. So r is going to be, that's the magnitude of the complex number. Remember, magnitude of z. So that's going to be the square root of 1 plus 1, or 1 squared plus 1 squared, if you want to write it like that. And that's equal to root 2. Then theta is going to be arctan of 1 over 1. That's just the arctan of 1. So it's going to be pi over 4. So we've got the two parts that we need to write the polar form. So let's just put everything together. So z is going to be the r value, okay, so root 2, times cos theta, but theta is pi over 4, so cos pi over 4, plus r sin theta again, so pi over 4. Okay, so that's the polar form. So we've written it in terms of this radius value and the theta value. And if you simplify this, you'll get back to the Cartesian form 1 plus r. Okay, so there's a couple nice properties that this polar form has, and that's with regards to multiplication of complex numbers and division of complex numbers. Okay, so nice properties of polar form. Okay, so the first one is with regards to multiplication. So number 1, if I have z1 times z2, okay, the product of two complex numbers, we know how to do that in Cartesian form, and doing it in polar form is very simple as well. It's going to be r1 times r2, and then it's going to be cos theta 1 plus theta 2 plus r times sin theta 1 plus theta 2. Okay, so when we are multiplying two complex numbers, the magnitudes multiply. Okay, so we multiply the magnitude. And then this angle that we have with the complex number, we usually call that the phase. Okay, so this theta value is called the phase. The phases add. And over here as well. Okay, so we could write this as a new complex number. So R1 times R2, let's call that R. Theta 1 plus theta 2, let's call that theta. Okay, so we see how these magnitudes multiply to give us R in polar form, and then the phases add together to give us the new phase in polar form. Okay, so that's what happens when we multiply complex numbers. The magnitudes multiply and the phases get added. Okay, what about dividing complex numbers? So number 2, Z1 divided by Z2. Okay, now again, we know how to do this using Cartesian form. How do we do it in polar form? Well, in the previous case, the magnitudes multiplied when we multiplied the complex numbers. When we're dividing them, the magnitudes get divided. Okay, and then we have cos theta 1 minus theta 2 plus r times sine theta 1 minus theta 2. Okay, so it's a bit opposite to what happens when we multiply. So here the magnitudes divide, they get divided. Okay, and the phases get subtracted. Okay, so it's like an opposite of multiplication. So with multiplication, the phases get added. For division, the phases get subtracted. Now, this only applies, these nice properties only apply to multiplication and division. If you were to add two complex numbers or subtract two complex numbers in polar form, it wouldn't look so nice as this. Okay, so these nice properties of adding phases and subtracting phases, that's only for multiplication and division. Okay. Okay, so the next thing that's going to help us with taking powers of complex numbers is Euler's formula. Okay, so I'm just going to write it down without any proof. So we're going to look at it in more detail later on when we do complex functions, and then we will prove it towards the end of the semester when we do Taylor series. Okay, but for now, we can just write it down without proof. Okay, so, sorry. Okay, so Euler's formula. Okay, so the explanation and the proof, that will come later. But for now, we can just use it as a tool. Okay, so Euler's formula says that e to the r theta is equal to cos theta plus r sine theta. So what we're doing here is we're taking the standard exponential and we are extending it to complex numbers. So we know that e to the x works for x being a real number. Okay, we know how to calculate that. So x can be a positive real number, x can be a negative real number. We can deal with e to the x. Now what happens here is we extend this to complex numbers now. So we're going to have e to the z, where z is now a complex number. Okay, so the exponential function has been extended. Okay, so the domain's bigger now. Instead of just having the real numbers as the domain, this complex exponential now has the complex numbers as its domain. Okay, so remember Z can be, it can have a real part and an imaginary part. Here we're only dealing with the imaginary part. Okay, this e to the r theta part. Okay, but that's fine, because if we rewrite this, e to the z, that's the same as e to the x plus ry. We can always just split this up, the x and the ry, using exponential properties. So that's e to the x, e to the ry. Okay, so that's e to the x. And then this e to the ry, we know how to calculate that now using Euler's formula. So that's going to be cos y plus r sine y. Okay, so this is just a short introduction to the extension of the complex exponential. Okay, so that's part of that there. Okay, but we're just going to be dealing with this e to the r theta part, where theta is a real number. Okay, later on we will look at e to the rz, where z is any complex number. Okay, so how is this helpful? Well, let's write this out again and try to find the power of a complex number using Euler's formula. Okay, so if we have some complex number z, in polar form, we know we can write this as r cos theta plus r sine theta. Okay, so that's from before. But cos theta plus r sine theta, that's going to be e to the r theta using Euler's formula. So that means z is equal to r e to the r theta. Okay, so that's just another way of writing the polar form. So let's make a note. Another way of writing z in polar form. Okay, because we still have the r and the theta, so it's still polar form. It's just written a bit differently. Okay, so now we want to find z to the n, because we want to do powers of complex numbers. So z to the n is going to be r e to the r theta to the n. Okay, just take n on both sides. Now this n can be distributed inside. So we're going to get r to the n times e to the r theta to the n. Okay, the n can go on both sides. But now with this exponential, the n being an exponent can get multiplied inside. So this is going to be r to the n, e to the I n theta. Okay, so that's how we can take powers of complex numbers. So z to the n is equal to r to the n, e to the I n theta. Okay, so that's if you want to leave it in polar form. If you want to go back to Cartesian form, we just need to use Euler's formula again. So in Cartesian form, we can write z to the n is equal to, this r to the n we can keep outside, e to the I n theta, that's going to be cos n theta, plus r sine n theta. And then we can just identify the real part as rn cos n theta. So that's our real part, like x that we had before. And r to the n sine n theta, that's going to be the imaginary part, like we had with y before. Yeah, so we can write this in Cartesian form, x plus ry if we wanted to. Okay, so let's have a look at an example of this. So example, let's say we wanted to calculate 1/2 plus r times 1/2 to the power 10. Now, from before, we know how to multiply complex numbers. We just have x plus ry times x plus ry if you want to do it squared. However, this is to the power 10. So you're going to have to write this out 10 times and then do the multiplication. That's going to take forever. So instead, we're going to use this technique here of using the polar form. Okay, just to make things a bit easier. So first, we need to turn this complex number 1/2 plus r times 1/2 into this polar form, the r e to the r theta. So we need to find r. So r is equal to the square root of 1/2 squared plus 1/2 squared. So that's the root of 1/4 plus 1/4, which is root 1/2, which is 1 over root 2. Okay, so we got the value of r, and theta is going to be arctan of 1/2 divided by 1/2. Okay, because y is 1/2, x is 1/2. So that's going to be arctan of 1. That's just going to be pi over 4. Okay, so we've got the r value, we've got the theta value. So that means we can rewrite this as z is equal to 1/2 plus r times 1/2. Okay, in Cartesian form. In polar form, this would be 1 over root 2 e to the r pi over 4. Okay, using Euler's formula there. Now, if we want to calculate this complex number to the power 10, we can just use this formula that we came up with over here. Okay, so z to the 10 is going to be r to the 10. So 1 over root 2 to the 10 times cos of 10 times pi over 4 plus r sine 10 times pi over 4. Okay, because it's n times theta in both cases. So we can simplify this. 1 over root 2 to the 10 is the same as 1 over 2 to the 5, so that's 1 over 32. Cos of 10 times pi over 4, we can simplify that to 5 pi over 2. Plus r sine, again, 10 times pi over 4. That's going to be 5 pi over 2. Okay, and lastly, we can simplify this cos of 5 pi over 2 and sine of 5 pi over 2. We're going to get 1 over 32 times r. Okay, so it's just an imaginary component to this z to the 10. So there's no real part. Okay, just I over 32. Okay, so the method is not too bad. You just need to take your complex number, write it in polar form, and then use this equation in the green box to find the nth power of that complex number. Okay, let's look at another example. Okay, so let's say we have 1 minus I root 3 to the 5th power. Okay, so it's this times itself 5 times. So again, the first thing we need to do is write this in polar form, so that's going to help us with the calculation. So r is going to be the square root of 1 squared plus 3. So that's going to be root 4, that's going to be 2. Theta is going to be arctan of minus root 3 over 1. So that's going to be minus pi over 3. Okay, so we've got the r value, we've got the theta value. We can now write this in polar form and then take the nth power of that. Okay, so if we just say that z is equal to 1 minus I root 3, we want to calculate z to the 5. So z to the 5 is going to be, again, r to the 5. Okay, so that's going to be 2 to the 5. Then we're going to have cos of n times theta, but n is 5. So it's going to be minus 5 times pi over 3. plus r sine, again, minus 5 times pi over 3. Okay, so we can simplify this and then work out what each one is. So 2 to the 5, that's going to be 32. Cos of minus 5 pi over 3, we can just write that as cos of 5 pi over 3, because cos is even. And sine of minus 5 pi over 3, we can write that as minus r sine 5 pi over 3, because sine is odd. And then it's just a matter of simplifying these two. So we get 32. Cos of 5 pi over 3, that's going to be 1/2. Plus r times root 3 over 2. Okay, then we can finally distribute the 32 inside, and we get 16 plus r 16 root 3. Okay, so that's what we get for this complex number raised to the power 5. Okay, so this procedure works for any positive power of n. Okay, so if you want to square something, cube something, raise it to the power 10, this works perfectly fine. Now, if this n is a fraction, then what we're doing is we're taking the root of a complex number. For example, 2 to the 1/2, remember that's the same as root 2. Or 2 to the 1/3, that's the cube root of 2. Okay, so when n is a fraction, that means we're dealing with roots. Okay, so let's have a look at those cases. Okay, so if n is a fraction, then we're dealing with finding the roots of a complex number. Okay, so something like the square root of z or the cube root of z and so on. Okay, so the method for finding the roots of a complex number is very similar to finding the power of a complex number. So we start off with z is equal to r e to the r theta. Okay, we start off with the polar form. Then we take the nth root on both sides. So the nth root of z is the same as z to the 1 over n, if you want to write it like that. This is equal to r e to the r theta to the 1 over n. And much like before, when we had n distributing inside, we can do the same thing with 1 over n. So this is going to be r to the 1 over n, e to the r theta over n. Okay, now I'm just going to put a little star here because this is not, it's not the complete formula. We need to remember that e to the r theta is in fact 2 pi periodic, because e to the r theta is cos theta plus r sine theta. Cos theta is 2 pi periodic. Sine theta is 2 pi periodic. So e to the r theta is also 2 pi periodic. So if we write it in this Euler's form, this function being 2 pi periodic is the same thing as saying e to the r theta is equal to e to the r theta plus 2 pi k, right, where k is some integer. Okay, so if you have cos and you add some multiple of 2 pi to the argument, you get back to where you started. The same thing happens with e to the r theta. If you add a multiple of 2 pi to the argument, you get back to where you started. Okay, so what we need to do is incorporate this into the formula here. So this bit we need to substitute inside. Okay, so what we get is r to the 1 over n, e to the r, sorry, there's brackets there, e to the r theta plus 2 pi k over n, where k can be some integer. Okay, but in fact, when we're finding the roots of a complex number, we're not going to take all values of k, like infinitely many, because k can be an integer. Here, k starts from 0 and goes up to n minus 1. Okay, so if k is 0, that's going to give us the first root. K equals 1, that gives us the second root, all the way up to k equals n minus 1. That gives us the nth root. Okay, so in fact, when we take the nth root of a complex number, we get n possible solutions. Okay, so a little note here. We get n solutions to the nth root of z. Okay, so before, when we took the power of a complex number, z squared had one solution. However, if we're taking the root of a complex number, we get n solutions. Okay, so we say that they are the nth roots of the complex number. So n solutions, or we say the n roots of the complex number. Okay, so if we're taking the cube root of z, we're going to have 3 roots, 3 solutions. Okay, let's have a look at an example. So example, find the sixth roots. Okay, so z to the power 1 over 6, the 6th root of z is equal to minus 8. Okay, so since we are taking the sixth root, we're going to have 6 solutions to this. Okay, so the first thing we need to do is write this complex number z in polar form. So z is equal to minus 8. Okay, so we want to write this as re to the r theta, where r is positive. So r is going to be 8 in this case. And what about theta? Well, theta is going to be pi. So we can write this as 8e to the r pi. Since e to the r pi is minus 1. Okay, so you can substitute that into Euler's formula, and you see that we get minus 1 as a solution. Okay, so minus 8 is 8 times e to the r power in polar form. Okay, so now we want to find the 6 roots of this. So let's say that the roots are given by w. So let wk be the roots of z. Okay, just so that we can list them out. So we're going to have w0 up to w7. Okay, so there's going to be 8 of them. Sorry, w0 up to w5, that's going to be 6 of them. Okay, so what is this wk? Wk is going to be r to the 1 over n, like we had before, e to the r, and then we're going to have theta plus 2 pi k because of the periodicity, divided by n, and k is going to be 0 up to n minus 1. Okay, so we just need to substitute the 6 values of k, and that will give us the 6 roots of this complex number. Okay, so let's go through them. So w0, that's the first one. That's going to be 8 to the 1 over 6 because n is 6. So 8 to the 1 over 6. And then we're going to have cos of pi over 6 plus r sine pi over 6. Okay, so this is for k equals 0. So we just have this e to the r theta over n. Okay, so we can simplify this. 8 to the 1 over 6, that's going to be root 2. Cos pi over 6, that's going to be root 3 over 2. Sine pi over 6, that's going to be a half. Okay, so we have our first root, W0. Now we just need to find W1 up to W5. So W1, that's going to be 8 to the 1 over 6. Cos of, now k is 1, so we need to add one multiple of 2 pi. So it's going to be pi, as we had for theta, plus 2 pi, again over 6. Plus r sine, the same thing, pi plus 2 pi over 6. Again, 8 to the 1 over 6, that's going to be root 2. And then we can just simplify these. Okay, so cos of 3 pi over 6, we're going to have 0. And for the sine term, it's just going to be r. Okay, so that's W1. Let's look at W2. Okay, same thing, 8 to the 1 over 6. Cos of, now k is 2, so we're going to add 2 multiples of 2 pi. So that's going to be pi plus 4 pi over 6 plus r sine pi plus 4 pi over 6. Okay, and that's going to give us root 2. Then we're going to have minus root 3 over 2 plus r times a half. Okay, so that's W2. Let's look at W3. Again, 8 to the 1 over 6. Cos of, now k is 3, so we're adding 3 multiples of 2 pi. So that's going to be pi plus 6 pi over 6 plus r sine, again, pi plus 6 pi over 6. And we can simplify this like the others. So we're going to get root 2 cos of pi plus 6 pi over 6. That's going to be minus root 3 over 2. And then sine of pi plus 6 pi over 6, we're going to get minus r times a half. Okay, almost done. W4. 8 to the 1 over 6. Cos of pi plus, now we have 4 multiples of 2 pi. So it's going to be 8 pi over 6 plus r times sine pi plus 8 pi over 6. Okay, and again, we can simplify. So that's going to be root 2. This first part's going to give us 0. Second part's going to give us minus r. Okay, and last one, W5. Okay, because we go up to n minus 1. So W5, 8 to the 1 over 6. Cos of pi plus, now k is 5, so it's going to be 5 multiples of 2 pi. So that's 10 pi over 6 plus r sine pi plus 10 pi over 6. And we can simplify this. That's going to be root 2. This is going to be root 3 over 2. And then we're going to have minus r times 1/2. Okay, so these are our six roots of z, okay, of minus 8. So you can check if you want to. You can take any of these roots here, raise it to the power 6, and you should get back to minus 8. Okay, much like if you take root 2 and you square it, you get back to 2. If you take any of these and you raise it to the power 6, you get back to the original number z. Okay, but in this case, we get W0, 1, 2, 3, 4, 5. So those are the six roots. So W0, to W5 are the six roots of -8. Okay, so let's give you some homework. Find the 3 cube roots of 1. So that's the first part. Second part, plot these WK on the complex plane. Okay, so you're going to get 3 solutions. Put points on the complex plane. So plot them. And number 3, what do you notice? Okay, so you will see something very interesting when you plot these roots on the complex plane. So this is just the 3 cube roots of 1. You can try it out for the 4 cube roots of 1, and you will see something similar. Okay, so I don't want to spoil it too yet. So I don't want to spoil it yet. So give this a go. Plot them, and then just see what you notice if you plot the 3 cube roots, and if you want to try it out, the 4 fourth roots. Okay, you should see something, some sort of figure in the complex plane when you do that. Okay, but I will post the homework later on today so you can check your solutions. I will also post the diagram for the 4 fourth roots, so then you can see what happens in that case. Okay, so if you have any questions, you can send me an email or ask me on the WhatsApp group. The tutors are also available, so you can send them an email or ask them on the WhatsApp group as well. Okay, so remember that the Friday lecture period is cancelled because we're having that in-person lecture period on Tuesdays. Okay, so this Friday, we're not going to have anything. Next week, Tuesday, we will start with the Tuesday in-person lecture periods. Okay, we will carry on with this complex number stuff. Okay, so I'll see you then. Bye, everyone.